Good evening and welcome to our third Sysdig Meetup. The meetup tonight is about a cool, hopefully cool new software that we're going to release soon, which is called Csysdig. A couple of words about myself. My name is Loris Degioanni. I'm the creator and CEO of Sysdig. I've been involved in open source for half of my life at this point. For 15 or 20 years. In the past, I've done quite a bit of work in the networking space, especially contributing to tools like WinPickup and Warshack, and now Sysdig. We have a pretty dense agenda for the meetup tonight. As I was telling you, the meetup is centered around Sysdig, which is the extension of Sysdig, the user interface that extends Sysdig to give an interactive interface based on a console interface based on curses. We're going to have an overview of Sysdig and Csysdig, then a demo of Sysdig, then Gianluca will present a cool advanced use case which involves using Sysdig to hand processes hidden with LD preloads, so very good for geeks and more in-depth technical people. I will spend some words on the architecture of Sysdig that will also be the base to explain you the system, the engine that is the base of the customizability of Sysdig and the ability to create your own views. The whole session will be pretty interactive. We'll have demos with our Linux instances, so we'll be in front of our tools. Hopefully everything will go well, but don't worry, we have everything under control. What is Sysdig? How many of you guys have used Sysdig, the command line Sysdig? Okay. Around half of you guys. So a 3 minutes introduction to Sysdig. Sysdig is a tool to capture system events, filter them, run useful scripts. We often compare it to strace plus tcpdump plus lsof with the ability of writing scripts in low on top of that. Sysdig is completely open source and it's available on our GitHub repository. Sysdig was designed with few goals in mind, being production ready, which means being as simple as possible, especially the kernel level instrumentation part. We try to keep it as limited and straightforward as possible to prevent issues in the kernel, and lightweight, so efficient, so that you can run it essentially on any kind of system. Rich data, instant value, so being able to get value from the tool pretty easily, and the Sysdig interface goes toward the goal. Natural workflow and native support for containers. Let me give you the 30-second example of Sysdig. So if I run it without any parameter on the command line, I get this very useful and interesting and satisfying list of events on the screen on my console. Essentially, what happens is Sysdig hooks, the Sysdig kernel module hooks different places inside the kernel and extracts these events, decodes them, and presents you in a way that is sort of similar to something like a strace. The difference between Sysdig and the tool like a strace is that first of all, it supports filtering, so I can do something like file descriptor .name contains /etc, and at this point, let's generate some activity. I can capture only the activity on a specific directory of my machine. And I can also run scripts, which we call chisels, so I can do something like run a chisel called top procs CPU. And at this point, as you can see, this is essentially obtained by feeding the same list of events into a Lua script that then interactively presents the results on the screen every second in this case. What is Sysdig? So Sysdig is a simple, intuitive, and fully customizable user interface for Sysdig. As you can see, I have in black the things that are in common with Sysdig, so you can capture system events, filter them, run user scripts, but also visualize this information and interact with it. We also extended our comparison. Instead of just a strace plus tcpdump plus lsof, now it's also htop, iftop, iotop, and a bunch of tools, and of course still Lua scripting as well. Csysdig is, again, open source, fully available, not released yet, so you are getting a sneak peek during this meetup. We're planning to release it very soon, hopefully sometimes this week, if no tragedy happens, which is never the case in software, right? Design goals. One tool to rule them all. So this is sort of ambitious, admittedly, but it's like we come from the networking world where there are tools like tcpdump and Wireshark that are well recognized de facto standard tools that are sort of a lingua franca for networking, and you know that you can feed packets to them and get a bunch of stuff from them. While the space of system monitoring and system troubleshooting is much more fragmented. And we see this as a limitation, in the workflow of people that have to monitor and troubleshoot systems, Linux especially in this case, but also a limitation in productivity. One of the goals that we had when we came up with the idea of creating a user interface for Sysdig was, is it possible to have a single tool that can cover most of the use cases when you're doing system level troubleshooting? So process and memory, networking, file I/O, and disk I/O, and so on, errors, logs, and much more. Again, it's sort of an ambitious idea, but I will show you later that it's sort of cool how Sysdig starts trying to approach that idea. Support for both live and trace file analysis. This is another thing. Coming from networking, it's really nice to just run a trace file and not having to sit in front of your network while the problem is happening, essentially being decoupled from the event, the problem, the issue happening in front of you. And why wouldn't it be cool to have the same functionality with system level troubleshooting? So that's one of the design goals of Sysdig. An intuitive drill-down oriented user interface. The idea is being able to move quickly from the big picture to maybe the fine details, especially when you're trying to hunt a bug or something like that, or a performance issue. That's very important, and especially it's important to preserve the context. One thing that annoys me a lot is when I'm investigating something and I need to switch to a different tool, and so I lose essentially the information that I had, and I had to recreate and to go again to the same position. So we try to address that with Sysdig. Fully customizable. Everyone's need is different. We're talking about sophisticated needs here. So being able to fine tune it for your specific needs is often very important. And then container support. I left it as the last one, but to me is one of the most important ones. I am, and the rest of the Sysdig team is a strong believer in containers and what they can bring, to the world in terms of progress in how infrastructures are run. And it's quite interesting how, containers are pretty new, and visibility for containers is extremely limited. And within the world needs better container visibility, and we put quite a bit of effort in Sysdig and Sysdig to improve things. All right. Let's stop talking and let's show you guys the tool. Some things that typically people would like to monitor. So resource usage, file I/O, activity, network activity, application, errors, user activity, containers. So let's take a look. If I run Sysdig without any parameter, I get a user interface that refreshes once every 2 seconds. Probably people that use Linux on a regular basis or that are in the trenches clearly recognize an interface that looks a lot like the htop user interface. I am a big lover of htop. I use the tool, essentially it's always running on my machine. So when designing Sysdig, I wanted to get the same feel and also they get the same interactivity. So not only the look and feel is similar to htop, but as much as possible we try to preserve the same, for example, the same key bindings, so that if you're an htop user, for example, I don't know, you can do search with the same key, you can move around with the same keys. It supports horizontal scrolling like htop, which is a feature that I like a lot. So it tries to mimic the htop user interface, but for a reason, because we think it's very good, it's very effective, and we wanted essentially to start from there and enhance it. This is live in real time, but I can also work on a trace file, so I can try now. I'm running Sysdig now with the -r, and I'm reading a trace file that I captured on this machine in the past. So as you can see, same user interface. This time things are not moving, but again, looks a lot like an htop. The first big difference between this and htop is I can click on F2 or click on the views button here, and I get a selection of things that I can see. And as you can see, there's quite a bit of stuff. By the way, is this readable? Does it need to be bigger? Looks good. Okay. So yeah, you know, the default view shows me essentially again an htop or top view with the list of processes and number of threads, memory, amount of file I/O, amount of network I/O, amount of CPU, and so on. But again, I can select something like connections and see the list of connections in the machine. Again, this works on a file, but would work more real time as well. I can look at, for example, the list of files. I can look at the top ports on the machine, server ports, and so on. So I have more choice of what I can see with the same user interface. The other thing is, if I go back again on processes, these tool supports drill down. So again, here I'm seeing one of the columns that I'm seeing here is the number of threads. And for example, I can see that the top process here is MySQL and has 22 threads. I can click enter on it, and I'm now inside MySQL, and I'm looking at the threads inside MySQL. So essentially, as you can see, the tool automatically builds a set of filters to follow my investigation when I click into something. Once I'm inside MySQL, I can again click on views, and I have a bunch of things that I can inspect inside MySQL. So for example, the process connections, or again, the process files, or whatever else I want. Now I'm limited essentially in the scope of the specific process that I selected. This is cool. Let's do a couple of examples. Let's go back to the main machine. Let's do, for example, file I/O investigation. One of the views that I have, for example, is directories that I can use to see what are the directories that are more accessed on my machine. And as I can see, this is sorted by number of operations, but I see, you know, the number of bytes, the number of file opens, and so on a specific directory. As I was saying, I can, for example, hit F4 like in htop and search, for example, for etc. And now I'm, you know, looking at a specific directory, and I get the metrics for that one. I can, you know, click enter, and now I'm seeing the specific files that are that were accessed inside the /etc directory. Another unique thing about Sysdig is the echo button. When I do that, essentially what happens is the events for the selection that is made in this case, for example, /etc/host, are filtered and presented on the screen as a readable buffer. So I can do printable ASCII, and this is essentially showing me which data was read and by which process. So this was Apache 2 reading this file, and I can see which data was read by this file. Again, this is investigation friendly, so I can click on backspace and I can pick a different file, and I can see, for example, VM tools opening /etc/mtext. Yes?
By default, how long are we going back? Past 2 minutes, 3 minutes?
So, if you're doing real time, you're looking at the last 2 seconds. So you're looking at the data for the last 2 seconds. When you are on the file, this covers the whole file. So how much you go in the past depends on how long of a trace file you're taking, right? So this trace file is 7.95 seconds. The tool tells me, you know. It tells me how many events it has. So it's a relatively small file. I can capture as long as I want. I can capture, you know, for an hour. And at this point, when I investigate the file, the tool will show me the files will cover the whole file essentially. Because it just goes on all the events of the file and applies essentially the logic to the whole file. Does it make sense?
Yes. I would also think it would be a very nice tunable to go ahead and set a buffer at 10 seconds rather than just 2 when you do it live.
So when you do it live, you can do like htop. So I can do it something like it's D, right? And let's do 5,000, which is 5 seconds. So now refresh will be slower, but I'm accumulating for 5 seconds. I can go longer than that. At that point, it will move very slow and maybe take a bit of time to create the first sample. But I can pick any number I want. It supports anything between 100 milliseconds to infinity. Let's go back to the file. And let's do, for example, some networking investigation. So this time I move to server ports, and I'm seeing, you know, traffic on port 3306, which is MySQL. I see traffic on port 80, which is HTTP. I can again drill down, so click on enter for port 80, and now I have the processes that are generating traffic on port 80, right? Because this view drills down into processes. Let's sort by network I/O, and I can see, for example, that HA proxy is the process on this machine that is generating the most traffic, the most port 80 traffic. I can again click on echo, and I see requests and responses, printable ASCII. And this is the activity, the requests and responses made by HA proxy during this the time this trace file was captured. This is all the traffic, but I can keep drilling down. You know, I can go deeper, so I can click on HA proxy. Now and you see the tool tells me I'm on port 80 and process, which is the PID of HA proxy, and I can again click on views and look at a connection. So now I've broken down all the HA proxy traffic by connection, and I can go into an arbitrary one and again do echo, and I'm seeing only this specific connection. The other thing that I can do that is pretty cool is F6 or dig button. This is sort of a portable Sysdig only for the specific selection that I made. So I do it again. I pick a connection. I click on dig, and now I get Sysdig output for the specific connection. I can see the connect. So this is a connection leaving HA proxy. I can see the send to. I can see the data that is sent. I can see, you know, the first time received from, returned with not ready error, and the second time it actually received data. So I can follow essentially all the progress for the specific connection. So it's like the bunch of traffic that I was showing on the screen for Sysdig before, but this time I can interactively look at it only for limited portions of my trace file. In some cases, like this one, very limited portion. So I started from 208,000 events in this file, which is quite a lot, but here I'm seeing only 28. So again, quite good for investigating, even if you want to go in the deeper details. Other things that you can do with this and you cannot do with your traditional htop or other tools like this are views that are based more on like a deeper system investigation. One that I like, for example, is called errors. This one looks at all the activity that processes are doing, all the interactions that the processes are doing with the operating system, and monitors the one that are returning an error. In this case, for example, I see that I'm having a bunch of errors. These are irrelevant here again. This just means timeout, and it's not a problem. But inc means file not found, and I have 3,000 of them. So again, I can read down, click enter, and I see the processes that are generating these errors. And it's quite clear that two processes are generating most of them: an API server and MySQL. So again, I can select API server, and I dig into it, and it's quite clear. As you can see, these are a bunch of opens that fail and fail on this file, logs applog.txt. So this process is not configured correctly and is not finding this file, or the directory is not present, and so on. Same with MySQL. I can go and dig inside and see what's happening, and I can see a bunch of stats. Is just MySQL checking if the file is there, and it fails means that the file is not there, but there are also failed opens, under WordPress and so on. So again, probably something that there's like 3,000 of them in 8 seconds, so something that maybe I need to investigate. What else? Containers. As I was saying, if you are doing containers, using this tool is really going to change your life. This sounds a bit arrogant, but I know it's the case. There's very little stuff around to troubleshoot containers, and again, I go back to the home machine and I pick the containers view here, and I get the list of containers that are running on the machine. I get the CPU, the memory, network traffic, disk traffic, and so on. And this is where the drill down capability of Sysdig really shines, because I have a list of containers. I can jump inside one, for example, the WordPress container. And now I'm seeing the processes inside the container. This is not easy to do with traditional tools. But again, I can, once I'm inside the container, I can click on views, and I can, again, pick the connections for the container. I can look at which files the container is opening. And I can, again, investigate and look at the specific input-output on a specific file. So the ability of drilling down into a container tends to be pretty powerful, especially because once you're inside, you really have a broad range of things that you can monitor for the specific container. All right, let's switch to Gianluca, and let's
Good evening, everyone. My name is Gianluca, and we are about to get our hands very, very dirty. The goal of today is to take a process under Linux and completely hide it from the output of top, PS, htop, you name it. What I'm going to show is not meant to be a lecture in security, since it's pretty easy from a technical standpoint, so it's more of a nice use case of showing some Sysdig features. Let's get started. Let's start with PS. So we all know the output, right? And as I said, what I want to achieve is taking one of these lines and getting rid of it. How can we do it? The process that I'm going to hide is this one. I'm calling it evil script. It's essentially a little Python script that takes as an argument an IP and a port, and then it essentially sends in a loop a bunch of UDP packets towards that victim with the payload, I am a bad boy. So let's run this one. I'm going to run it on localhost, so the PagerDuty guys will not arrest me. And of course, if I run PS now, let's reduce a little bit here. Yeah, I can see that it clearly shows up in PS with this PID and all sorts of things. So if I want to hide this process, the first thing that I need to do is to understand what PS actually does, right? And there's not a better use case for this than using Sysdig. So I can create a Sysdig trace file, a simple Sysdig trace file using a large I/O buffer and saving it in trace.scap. And then I can run PS, and then I can terminate the capture. As Loris shown, this will essentially give me a trace file that contains all the execution flow for PS that I can analyze offline as much as I want, as many times as I want. And I'm going to analyze it, of course, with our new toy, Sysdig. So opening it, oops. All right. So opening it, of course, I can see that I have the evil script with this PID 3722. But what I'm interested in is PS. So I can press F4 and filter by PS, which of course is here because I ran it while this is the trace file was running. I can drill down into the view, and I have the thread view, which of course shows just one thread because PS is single threaded. I can drill down even more and then get to the file view, where I can see the files I/O ordered by number of I/O operation. Let's order by file name, which is as easy as clicking here. And I can see that, not surprisingly, PS is taking all of its information from the proc file system. In particular, under proc, we have a bunch of directories where each directory is named after the PID of one process in the system. And for each of these subdirectories, there are a bunch of files that contains all sorts of statistics for this process. So, for example, our evil script was PID 3722. So I can just F4 filter 3722, and here we are. So exactly 3 files are being accessed for getting information about evil script, and I can of course just see their content with F5 echo, and I can see that here the command line is red. Under stat, the name of the process is red, along with a bunch of counters that contain all sorts of things, CPU, memory, and other things. And status that contains pretty much the same information in a more user-friendly way. Of course, I can format with ASCII formatting. And so, in some way, if I want to hide this process from PS, I have to somehow prevent PS from reading these 3 files, or better, from reading this directory. How can I do that? First of all, how can PS discover these files, right? PS needs to do somehow inside this code the same thing as you would do on a shell. It needs to do ls_proc in order to discover these 3 files exist. So we can study a little bit how PS works. We can drill up with backspace, and we are back to the thread view. And here I'm going to go with F6 on the Sysdig view, which, as Loris shown, will show me all the events for the PS process in a raw way. And here I can do Control F, and I want to search for all the events that have something to do with proc. I can see that there are some of them, but immediately here I have one that catches my eyes. In particular, here I have the open app where the proc directory here is being opened, and immediately after I have this interesting system call, which is called getDends. This system call does nothing more than taking as an input a directory, which we can see clearly here, /proc, and as an output it will return me the list of files and subdirectories that are present in that directory. So what PS does is essentially calling this function, get the list of all the directories, and then starting iterating over them. In fact, we can see that immediately after it starts reading proc/1.stat, and after a little bit here it reads proc2 stat, and then it reads proc3 stat, and so on. So a possible strategy for my little game can be intercepting this getDends system call, and then somehow if I can manipulate the output, right, and if I can grab that list and filter the directory that corresponds to the process that I want to hide, then I'll be good to go. This is actually fairly easy to do. if you go read the documentation for the getDent system call, which is the one that I just showed you, it will tell you essentially what it does, and then it will say, usually processes don't call the getDent directly, the system call, but they use a wrapper function called readDir, which is defined in the libc, which is a high-level system library, which is more essentially user-friendly. So what happens is that when the PS program is executed on the shell, the PS executable is loaded into memory, and then a bunch of system libraries on which PS depends on are also loaded into memory. So when PS needs to get the list of directory, it will call the readDir from the libc, which in turn will call the getDents that we see here in the Sysdig output, which is the gate, which can see things at the gate between user and kernel. How does this happen? This happened clearly here. We can see this is the very first event of PS where we have its execution, and we can see that immediately after a bunch of system libraries are loaded. libproc PS, then we have libdl.so, and then we have finally the libc, which contains the readDir. Luckily for me, Linux offers a system where I can say, take this custom library that I write, so I program my own library, and then I can say, make sure that from now on, every time a process is loaded, load my custom library before the system libraries like libc. So if my custom library contains a definition of the function readDir, I can essentially manipulate its output and do whatever I want. And this is exactly what we are going to do. This works in a fairly easy way that we can see here. When the PS process is started, the first thing that we'll look for is this etc/ld.so.preload. It's a file that is supposed to contain all the list of custom libraries to be loaded before the system wants. So let's leverage this. Let's step out of Sysdig for a minute, and let's enter in libprocess_hider, which is my custom library. And as I said, this is some very simple C code that essentially contains a definition for the readDir function that has the same prototype of the one from the libc, and will do nothing more than, as I said, call the original readDir function from libc. Then it will get its output, and if readDir is about to return a directory under proc that corresponds to a process name for which the name of the process itself is equal to this process to filter variable, which is set to evil script, then it will just filter out completely the output of the function. So this directory will be invisible to PS itself. Let's go ahead and let's compile this. So after it's compiled, I have a libprocess_hider.so, and then I can install it. So let's install it under user local lib. And then, as said before, let's enable it system-wide with ld.so.preload. Was already here. I'm just going to decomment it. And from this moment on, even if evil script is still running, if I type PS, it's gone. So it worked. We completely hid a process under Linux. And since this is generic, this not only just works for PS, but I can run, for example, htop. And I can press F4 filter by evil, and there's nothing. So this is completely hidden from the system. It's pretty interesting to analyze the situation from a low-level point of view. So I'm going to do exactly the same as I did before. So I'm going to create a Sysdig trace file where let's run again the evil script, and let's run PS, which of course doesn't show evil process. And let's stop Sysdig and let's analyze the trace file. Sysdig trace.scat. Interesting enough, we can see that evil script still shows under Sysdig. Why is this? This is because Sysdig, as Loris shown, take all the information from the system calls. So doesn't care if the entry about this Python process doesn't show up under proc. So with this little trick, we didn't fool Sysdig essentially. In fact, I can drill down in the Python process and see the thread view, and I can click on F2 and see the connections for the Python script. In fact, I can see that there's a stream of UDP towards localhost port 123, and of course I can click F5 echo, and I can see all the payload, all the full I am a bad boy, I am a bad boy, that keep repeating themselves very fast. But what is interesting to see is, let's go up and let's go back to PS, to the new invocation of PS. Let's drill down and let's go back to the system events with F6. In this case, now we can see that when PS is started, here, ld.so.preload is read, and this time lib process hider is actually loaded into memory before libc, which is loaded here. So this is how we discovered that there's something wrong with our binary. And another interesting thing, I can drill up and I can again drill down in the file view, and of course I can see all the processes under proc, and there's like before, it seems like PS is reading 3 files, and one is the command line. Oops. Yeah, I picked the wrong process because this one was a kernel thread. So, okay. And here I can see, for example, the command line, and under stat, this time, I don't know if you paid attention, but it seems like the stat file is read twice. Whereas before, if you remember, when I first drilled down in the able script, stat was read just once. Why is that? This is because the first read is done by my own lib process hider library implementation. If you remember, in that loop, there was an if this directory matches this filter, evil script, then filter it out. And this is how my library does it, because in the code, I go there and I read the stat file once, and then if I like the result, I return it back to PS, like in this case. And so PS reads again the file. If I don't like it, like in the case of evil script, everything will stop here and I will have just one read, and PS will never show me the output. And this is it. This was a little use case. I hope it was not too advanced, and to show how to see some cool stuff with Csysdig.
What I would like to do is spend a bit of time talking about the architecture of Sysdig and Csysdig, and after that essentially show you the concept of using Sysdig and how you customize the tool. From the, let's say, the event capture point of view, Sysdig is based on an architecture that is very similar to the architecture of packet capture tools. So there's a kernel module that intercept through a mechanism called trace points events inside the kernel, puts them in a shared buffer, and then pipes these events to user level where they are consumed by a series of libraries. So from the instrumentation point of view, it's like there's stuff coming from the kernel, goes in a buffer, and that's the only thing that this kernel module does, and then all the logic is at user level. How does the logic work? Let's pick an example of an event that Sysdig support, for example, a system call, for example, opening a file. This is what is called in the kernel when a process running on top of the operating system opens a file. And open requires a name and a set of flags and returns a result. The whole trick and what essentially enables all the advanced things that we do in Sysdig and Csysdig is based on what I called, I don't know if that word exists in English, probably not, but system event packetization, which means we take something like a function call inside the kernel and we convert it into something that looks a bit like a network packet, in the sense that it's structured information in which, for example, for an event like this, there's the process ID, the type of event, in this case it's open, the number of arguments, which is essentially how many fields I have for this specific event, which is 3, and then the 3 events. The first one is called res, and it's of type file descriptor. The second one is called name and is of type string, and the third one is called flags and is of type integer. Okay, so take a call and make essentially a little structured buffer out of it. This is what goes essentially in the shared buffer that then is shared with user level. And this is essentially the work that the driver does. Now, at user level, you start having a stream of events like this. You know, each row here is a different event. So in this case, for example, I have a very simple interaction which has, you know, an open event, two write events on the same file descriptor. So the file descriptor name, the number that is returned is 13. And then the two writes operate on the file descriptor and write, you know, buffers, hello world. And then there's a close system call that just closes the file. The first benefit of having this kind of structured structuring around the information in the kernel is that then it's very easy to process it with tools. The computers can process it. So I can do a couple of things. One is I can print this data on the screen, or I can filter this data. Let me switch again, and let me go out of it, and I can do, again, Sysdig without arguments gives me everything, but I can apply a filter, and I can do event.type equal close, and at this point I get only the close events that are happening on my system. How's that done? Very simple. Essentially, there's a stream of events like this, and it's just a matter of essentially doing a match on the second column of this, right, on the event type. So at the point, the system is pretty straightforward. The system becomes a bit more complicated when we're talking about enriching these events, because if we go back to this list of events, like I can filter on file name because there's an argument for the open system call, which is the file name, but that would work only for open, right? Because write or close just take the FD, which is a number, which is the number that open returned. So there's no clear match that enables me to just get all the events for a specific file. How do we do that? Essentially, we do that by capturing the events and creating a state that mirrors the state of the operating system as the capture progresses. So if we intercept that there's an open, we take note of it. If the result is positive, we remember the number and we put it in a table together with the file name and the fact that that specific file descriptor is a file and in the name of the file descriptor. If it's a socket, at that point it will go on the table with the flag that it's a network connection and with information about the network connection. At that point, I'm more flexible because I can apply better filters. So I can do I can apply a filter for file descriptor name as I was doing before. fd.name contains /etc, and at this point I get everything. You know, as you can see, I have the close. I have because the file descriptor is remembered. So this state system is the examples that I gave you are pretty simple and pretty elementary. On the other hand, Sysdig is has a lot of fields that are exported this way. As you can see, I have some examples here, but I can address a file descriptor by file name, by port. I can see if it's a server. I can use the environment variables or the number of threads of a process, the amount of memory, the thread ID of a thread, or even the ID that the thread has inside a container, latency, container name, username of a specific event, and so on. So the system is pretty rich and pretty sophisticated. All right, you can even create your own fields if you want. It works very similarly to how you would create again a dissector for a tool like tcpdump or Wireshark. Essentially, You have these streams of be called. You can have a callback that is called and returns a value, an arbitrary value, whatever you want. Okay, so the system is extensible. Now, what does this have to do with Sysdig? Sysdig. Why am I talking about this? Now that you understand the system, it's pretty clear how you can create a generic sort of mini MySQL for your system based on these fields. You just need essentially a filter that you can apply to the events that are coming from your kernel or from a trace file. You have a field extraction system, so you take the same fields that I was talking about, all of these fields that I was listing, and you're able to essentially instrument the tool to extract some of these fields and put them in a table. So for example, this is a very trivial example in which we extract two fields. One is a file descriptor name, and the other one is the buffer length, which is available for events that are I/O events, and essentially gives me the size of the buffer that has been read or written by the specific event. And then you can tell the tool, okay, I want the first field to be the key on the table, and I want the second event to be aggregated with an operation of sum, so that each time there's an event for the key, sum the value. And then essentially every X seconds, for example, every 2 seconds by default, everything is dumped to screen, and then you clean the table and you start again. So this is essentially a Sysdig view. Very straightforward in concept. Questions? Comments?
What's the language you use for scripting?
We use Lua. So I'm going to switch to my Linux now and show an example. Other questions? All right. This is a Sysdig view. This is a view that I created just for this meetup, so you guys should feel very lucky and very proud of yourself. It's called etc open count, and as you can see, it's essentially a little Lua program, and the view is expressed by default as a Lua table, whose syntax is very similar to something like JSON or something like that. So it's a structured way to represent your information. Views. The view format is documented on our wiki. The page is still not linked to the wiki, but it will as soon as we release the thing. But as you can see, it's pretty explanatory. So you have an ID which can be used to call that view from the command line directly without having to drill down and move and so on. You have a name. You have a description. You have tips that you can add to the view. So the view is sort of self-described, and is self-documented. So the documentation of the view is contained in the view itself. You have a view type because there are two types of view. One is table, which is more like a SQL table, and the other one is a list, which just appends, every time you add an item, it appends it to the end. You specify the filter, you remember? This is this filter here. And then you have the fields that you can apply this view to. So you can tell, I want to apply this view to processes. I want to apply this view only to connections. And the tool will understand this and will present the view for you only in the context where you specify. So for example, for the specific view, I have an empty, which means I want to be able to apply this to the whole system, and then I want to be able to apply it to processes. This is the drill down target. I will get into it later, but essentially it's to tell which view I want when I click enter on an item on this specific view. So where do I want to jump? And then, just a bunch of columns. So for each column, this is the key column, which is the PID, the process ID of the process. And then I count the number of events, and I print the username and the process name for the specific event. So I'm filtering by event type equal open, and file name contains /etc. So I'm only letting events that are opens and opens for files that are in slash etc go into my accumulation engine, and then the engine just counts these events and prints the user and the process for these events. So let's save this view. I saved it in my home directory. There's a specific directory where I can add my views, and let's run Sysdig again. Click on F2, and this is my view. The documentation appears on the screen, so this is what I had in the view. So it's nice because all the information that I put on the view itself appears on the screen and is presented by the tool, and then I can just execute it. And here I see, open count and user and comment for the opens that are in slash etc. As I was saying, this supports drill down as well. How does drill down works? Essentially, I have a table, right? A table with a key and a value. The key is the unique identifier for each entry in the table, and it's a field. It's a Sysdig field, right? So we go back to the type system that I was describing before. So when I click enter in on a line in a Sysdig table, Sysdig takes the field, creates a filter through that field by matching the column name and the row name, and then applies the new view with that filter. So in this case, I told Sysdig to switch to the files view once I click enter, so I can pick any process, and I click on it, and I will see the files that the process has opened under slash etc. And as you can see, Sysdig creates the filter automatically. So event type equal open, and that the name contains slash etc, and proc field is the field that I have selected. All right, I guess that's it. So again, I'm stopping for a second. There are questions or comments?
When you create views, you can only view the data within Csysdig, right? Do you have on your roadmap an ability to export it to say a REST API or a WebSocket or something like that?
Yeah, we have so many things in our roadmap, but yes, the idea would be being able to, for example, do a continuous export of this information. Another thing that we are considering is exporting maybe a trace file for the specific selection. So now you have an echo button and the Sysdig button. You could have a dump button that when you click it, your selection goes to a file, so you can post-process it later. So yes, I mean, but this lends itself very well to being able to do essentially continuous export of this information, which with the flexibility of being able to create views, as you can imagine, could be pretty powerful. Yes?
How heavy is the collection process on the system?
So,
like, would you run it on a production server?
How do I give you a 30-second answer? There are different components that are involved with this, and the whole architecture has been designed. If I go back to this slide, as I mentioned before, the collection is performed by the driver, and this is designed to be as simple and as efficient as possible. The main reason is making it production friendly. We share the same driver with our commercial product, which is called Sysdig Cloud, which is designed to run 24/7 with minimal overhead. So the driver is really designed to be number one, super stable, and number two, super lightweight. So the instrumentation is very lightweight and depends on essentially the overhead on your system. So it's hard to estimate, but in most of the typical workloads, you shouldn't even be able to measure the overhead of the driver. The driver is designed to do just one thing: take these events, copy them into the share buffer, and then move on. If the share buffer is full, drop the event, because you don't want to block essentially the instrumented application. So the overhead of the driver is extremely low, and the driver is designed to be extremely stable. Now, on top of the driver, there's a stack of things, and these don't really impact they don't slow down your application, but they can use CPU, And so the amount of CPU that they use totally depends on what they're doing. So even just with Sysdig, a heavy view that has many columns takes more CPU than a view that has maybe only 2 columns. Overall, what I'm seeing is Sysdig on a system that has a average workload, so not completely, not like nothing, but also not like I don't know, Redis doing 80,000 requests per second, but something normal. So a web server serving, I don't know, 500 requests per second or something like that. The overhead of Sysdig running is probably between 2 and 8% of the CPU, depending on the view that you run. Usually around, let's say, a ballpark of 2, 3, 4% of CPU, something like that. Again, this is just CPU used at user level. This is not a slowdown on your process. Sorry, it took much longer than 30 seconds. Other questions? By the way, another thing about that is, one thing that you can do is just dump all the files, all the events to file if you don't want to overhead, and then analyze them later. You can even dump them on a memory mapped file or something like that to make it more efficient. The point should be very lightweight.
Yeah, so I'm thinking I want to dump when something happens. For example, like when there's an issue with the system, create a dump and analyze it later.
Yeah. So a couple of things there. One is, if you know when there's an issue on the system, you can essentially execute Sysdig to make a trace file at that point. Number 2 is for the open source Sysdig, I think we have an issue on GitHub for somebody requesting essentially trigger-based capture, which is something that, again, if you go back to the type system, it would be possible to specify a filter to start the capture and a filter to stop the capture. It's not implemented yet, but again, it's a matter of resources, and of course, we always welcome contributions from the community. It's actually probably not too hard to build something like that. Number 3 is we have a open source, a commercial tool called Sysdig Cloud that actually enables you to do distributed Sysdig capture on your infrastructure. There's an API for that. It's not public yet, but that could be another way. As soon as we publish this API, you could use that to take your trace files based on triggers alerts, or whatever you want. Other questions, comments? So, yeah, my last slide is what are you waiting for? The only thing that I didn't mention is deploy is extremely easy. It's as you've seen, using the tool should be very easy. You guys tell us, but we really made an effort to design it to be as natural and as powerful and as intuitive as possible. Extending it to customize it for your flow is extremely easy. So I promise that in 3 minutes you will be able to go from this to this. Thank you.